マーティン・トンプソンさんで、関数型プログラミングによるパフォーマンスです。ではよろしくお願いします。
Good morning, everyone. So I'm going to start off. I'm going to ask you some questions, and I'm not going to talk about Scala, but I will talk about functional programming because I'm secretly a functional programmer who spends most of their life writing Java, C++, C, even assembler. So it's kind of like a little bit of an odd world. So let's just see if everyone's awake, and we'll sort of do some questions to begin with. I might speak a little bit fast, so please just shout and tell me to slow down if I'm speaking a little bit too fast. I've had lots of coffee this morning. I only slept 3 hours last night with jet lag, so I might be running a little bit slow. So, quick question for you all. Yeah, can someone turn up the volume a little bit, please? So we can hear. So, if we're going to access memory, are all memory operations equal? So, what I'm talking about is that we think we're going to access memory. It's going to be similar if I access 1 byte versus a different byte somewhere in memory. Are they all equal? It's a kind of really interesting question because we tend to believe memory is all the same. That's what we're led to believe. Algorithm theory talks about numbers of memory accesses. But let's start testing this out with some different ways. So let's walk through memory through a very large array, say a 1 gigabyte array in size, and I want to walk through touching every individual slot. And for each of the slots, let's add up the values that are in there, so we'll get a summation over all of the values inside the array. The question is, how long will it take per operation or per step through that array to do this? Any guesses out there? Anyone think it'd be milliseconds? Seconds? Microseconds? Nanoseconds? Well, you might be surprised at the answer. It takes less than 1 nanosecond per step to do this through an array. And this is the result of running a microbenchmark testing exactly that. Well, you might sort of start thinking, really? 1 nanosecond per operation? Like that's 1 billionth of a second. And if we've got a CPU that's running at, say, 3 gigahertz, that's only 3 cycles. Can we do that all in that period of time? Because you think what you've got to do, you've got to read the value of the slot, add it to the previous value that you've got to increment the slot index for the array, move on to the next one, load that, and get ready to go again. There's multiple things to be done per operation. So how can we do this so quickly? Well, if you look inside our modern CPUs, we start to see that they're much more complicated than people realize. Our CPUs can do many things at the same time. This is a Haswell Intel CPU, and it's got a scheduler inside a CPU core. This is inside the hardware itself, not the operating system. And you'll see from this picture that there's 8 ports on that scheduler, so it can be doing 8 different instructions at the same time. We start to realize how our code is written. We can be doing multiple things at the same time. So think of that array where I'm going to walk along the array. So I'm going to add up the value that's in the slot. I'm going to increment the loop counter from moving to the next slot. I need to read the next piece of memory. I need to write back the result of what I'm doing. Those are all different operations, but we can do a number of them at the same time. For example, we can be incrementing the accumulation we have of the values at the same time as incrementing the slot index for where we're going next. So that's multiple things happening at exactly the same time. And that's fine as long as we have no dependencies between those. So if there's no data dependence between the different operations, our CPUs will do them at the same time and give us greater throughput. But it gets a little bit more interesting. What if our pattern of access is different? And so I've tested a number of different patterns. What are these patterns? So we had to sequentially walk through an array from beginning to end. What if we go through the operating system pages? So within our memory, it's divided up into pages. They're 4 kilobytes in size typically. If we stay within one 4 kilobyte page and randomly go around different slots, adding up all the values, but do the same amount of work as if we went through it linearly, And then we'll move on to the next page and randomly go around it again, and then next page, until we've done the same work, but just in a different pattern. Or how about we'll go randomly within those slots, but we don't work out the next slot value until we know the value of the previous one. So there's a dependency in what we're doing. These are different patterns of access. Going right through to the end, where we'll look at, rather than just go around operating system pages, we'll go around the entire heap space that is the array. So I'll be jumping randomly everywhere all through here. Now, I can do the same amount of work. I won't use more CPU instructions to do this, depending on the different patterns of access. But the pattern of access makes a huge difference to our performance. Our CPUs are running instructions. You're typically, on a modern CPU, retiring between about 3 and 4 instructions per cycle. So that's less than a nanosecond per instruction. But if we look at the times to access memory, they're going up significantly, and the pattern of memory access matters. If we look at the worst case scenario up there, to go randomly within the whole heap, dependent on the previous value we looked at, we're at 90 nanoseconds, as opposed to less than 1 nanosecond if we're looking at things more locally. So that is quite a big difference. You start to realize that when you write code today, the cost is not measured in the number of instructions that you execute. It's in the memory access patterns that we take. And our data structures are a big influence on that. So how do we end up doing that? So I'm going to cover some mathematics here as well, just to see if everybody else is even more awake with this. So another little quiz for you. What is that? Anybody recognize that formula? That is the formula for queuing theory. One of the ones for an MD1 style queue, where we're trying to work out the average time you'll spend waiting for something to be done. And it's a function of the time it takes to process a single thing and the amount of utilization we have of a given service. So understanding how we use our services, understanding how busy they are, really dictates how responsive our system is. And particularly from this, the row in this, the utilization, is a function of the arrival rate times the service time. So the time our service takes to operate makes a large difference. And what does this look like if we start to graph it? So if I plug some figures into this, we typically see these sorts of graphs. Whereas we increase utilization, so going along the x-axis, the response time stays pretty constant until we start reaching a point where the graph ticks upwards. And this is where we start to have queuing effects in our system, so the thing gets busy. So we can't overutilize something. To use a simple example, let's say we do a job, and that job takes 100 milliseconds. If we have one job arriving per second, we're using 100 milliseconds off the second, so we're running at 10% utilization. If 5 things are arriving per second, we're using 5 times 100, we end up using half a second, so we're at 50% utilization. So we've got to look at how much we're utilizing anything, and as we increase the utilization, we end up queuing and we get these effects. What's this look like in the real world? Well, last year I was in India and I managed to get this photograph at one stage. This is what the road systems look like there because they're overutilized. We use it too much. I had a similar experience arriving here in Tokyo coming from the airport. If you put too many cars on the road, you eventually get gridlock and things don't move. The same thing happens to our software. We've got to consider what the utilization is, so we've got to be able to measure how often do things arrive and how long does it take to process a single job. From there, we can work out how our system's going to respond, how we don't get into this situation. So here's another one. There's another formula. Anyone guess what that is? Probably less well known. It's a thing called universal scalability law. And it's one of the best ways we have to predict the performance of any given system we have. The major components of this is the contention and coherence penalty. Contention penalty is for our given resource, how much are we using that from multiple threads or multiple processes, so we're contended on using that. This is Amdahl's law, you'll hear in another term. So we're working out what is the contention penalty of doing something. What's more interesting with this is how do we get agreement around using that contended resource? And that is what is coherence of this. I think a good way to think about this, if you're trying to work out how to cost something, imagine you're working in a team and everybody has to code review everybody else's code. If you have a team of 2 or 3 people, it's very easy for everyone to code review everyone else's code. If you have a larger team, we end up with a problem with the number of people squared. So it goes up, so it's easy in a small team, it becomes very difficult in a large team because the cost of agreement goes up quite significantly, and that's what comes out of this formula. If you were to plot that on a graph, this is what it ends up looking like, where we have something where we have got a job where only 5% of it is contended, the other 95% is not contended. We use additional CPUs. How do we scale up? We can only scale up to 20 times the speed. Beyond that, we can't go any faster because we cannot subdivide that 5%. But what if it takes a period of time to reach agreement between the various number of processors working on this job? That can start to dominate the cost as the numbers go up. And it reaches a point where that cost can even dominate and start to slow things down again. And this is becoming very common in our software. So when people talk about, say, a functional is going to cure the multi-core problem, not necessarily, because we have to get coherent agreement on some of the things that we're doing. And this starts to appear in our algorithms. What's this look like in the real world? Another picture from India. If we're going to get agreement, it's really important that we use a means of agreement that works and scales. What's interesting in this picture, see up here, that's a traffic light. And no one is paying any attention to it, and as a result, we don't have agreement. So we can't make progress. So we need efficient ways of reaching agreement, otherwise we're going to really slow down in this. So why does this all start to matter? Well, our CPUs, this is one of the latest AMD CPUs. Each of these little black blocks is a group of CPU cores. There's 8 CPU cores in each one of those blocks. Each of those have hyperthreads, so 16 threads per block. When you're communicating with inside that block, it's very efficient and it's very fast. As soon as you start going off that block or to the other side, we add time for agreement, so our things slow down a lot, so we cannot escape the mathematics of what's going on here. So we've got to think about what is the contended part of our algorithm and how long does it take us to reach agreement, because this will fundamentally dictate how well our software performs. So that's a bit of theory. Let's look at this from an engineering perspective, and we look at it from systems engineering. We've got to look at a system as a whole. We can't just understand our own little bit without realizing the implication of some of the other parts of our system. So I want to use a real-world use case of something I've worked on and know fairly well, and that's the concept of messaging. So when we're going to have different parts of our systems, they need to talk to each other. They can talk to each other by sending messages. Messaging is a very good way of doing communication because it respects that we are decoupled in time and space. So it respects how our software design works quite nicely. But it's got some really interesting problems in this space, that we have a lot of things that happen concurrently. Everything is distributed, and we have to think about things like networks and protocols and put this together. And then how do we apply this theory and the mathematics to make some of this stuff work? And so I want to look at what are the common approaches and how do we design for this. Now, particularly whenever you start sending messages on a network, they can go out of order. So you send messages from one machine to another. They may arrive in a different order you sent them. Some of them may be lost. Some of them may arrive multiple times. We need to be able to track that and put the order back together to be what we sent so we can trust our communications. Now, to do this, we typically use a number of different types of data structures. Things like skip lists, trees, scoreboards. But there's an interesting problem with all of these type of data structures. If you look at how these data structures are put together, there's nodes with pointers to other nodes, and we've got to follow these pointers. Following each of those pointers are the data-dependent loads that I was talking about that were taking 90 nanoseconds plus at a time. These are the most expensive operations we have. And here's some bad news for people who really love functional programming. Virtually all of the functional data structures, they all use these types of structures. They're all based upon different tree structures, different linked list structures, and this really hurts our performance. So we've got to think, how do we work with this? How do we take a systems engineering approach, respect what we know in the underlying hardware, but get some of the good things that we want to have in functional design? So how can we achieve that? We've got to look at ways of doing this, particularly the concept of immutability. So the way most data structures will implement immutability is it's a tree. Whenever you go to change the tree, you've got to copy one tree to another tree, preserve as much of it as you can, and swap the root node of the tree. So once you hold on to that root node reference, you've got an immutable view of your data structure that isn't going to change. But it's dealing with a lot of these data-dependent loads, which are the expensive memory operations. So how can we get around that? How can we think about dealing with it in another way? And if we start to do it concurrently, we're not just copying this, we're copying it multiple times and doing CAS operations on this. So you can't just go into building something that's going to work really well and really fast and have some of these characteristics and not have the consequences of the performance if you don't think about it. And particularly, you end up with this garbage collection hell problem because you allocate so many objects, they all have to be collected again later, and it starts to become another thing that slows you down because garbage collection is then got problems around agreement, it's got problems around dealing with contention on certain data structures to achieve that. So one way I like to think about it is we get these pretty data structures, and they may taste really good, they may really be nice to use, but within Europe, we can get sausages, and we can get different types of sausages. Now, from what I've seen of Japan appreciates quality. Inside your sausages are probably really nice, really good quality meat. This is not the case within Europe. We can get some that are really good, really nice quality, and some that are not so good. Some that got bits that have fallen on the floor and been put inside there, and maybe some things that are really not meat at all. And the way I like to kind of think about this is, if you actually start looking at building functional data structures and you look inside them, it's a bit like dealing with sausages. The more you know about what's inside of them, the less well you're going to sleep, the less you're going to feel comfortable about what's going on with some of this. So let's look at some of the theory and how can we apply some nice ways of doing this. So some really nice data structures we have at the moment are CRDTs, particularly working in the distributed space and concurrent space. There's different types of them, so let's very quickly cover some of them. One of the types you'll see is the commutative replicated data types. And this is where we can apply operations that can happen in any order. So rather than actually pass the state, if say for example I have a number and I want to have it replicated from one place to another, I can replicate the operations on it like add 1, subtract 1, whatever it happens to be like that. I can replicate those across. That's nice, and they can be applied in any order, and because they're commutative in supporting any order, that's a nice thing. That's particularly good in a network if we can deal with it because our messages can arrive in any order. Well, one of the things is these messages are not idempotent, or these operations are not idempotent, because if you sort of decrement something by 10 and you decrement it by 10 again, that has fundamentally changed what you're dealing with. It's not an idempotent thing. So it's actually not a really very good data structure for doing these type of things. Another type of data structure that we have is the convergent replicated data type. Behaves a little bit differently. The fundamental versions of it, you replicate the whole state from one thing to another, which is kind of an interesting problem in itself. But if you're going to do this, we need to look at how we deal with updates, and we need to deal with those monotonically. So things like we can monotonically increase or decrease state. We can't remove anything from the space. And to remove something, we've got to mark it in some way to say that this should not be used anymore. The technical term for this is tombstoning part of the structure. So we'll mark it as, we can't use this, we've got to move forward. And I'll give an example of this later. But what's kind of nice is these things support really nice merge functions where we can apply things in any order. We can apply them multiple times, it doesn't matter. We'll end up with the same state. We converge to the same state. This is the kind of thing you really want, designing a messaging system that's going to go across a network, because things will happen in any order. They'll happen multiple times. They'll get us to eventually the right state. And they don't require reliable transport. So if you're going to build a messaging system, you're building the reliable transport, so you can't rely on this. So some of the data structures I'm going to talk about are based upon the concept of convergent CRDTs. So Aeron is an example of this. So as I mentioned at the start, I'm a big fan of functional programming, but I live in a world where I don't use functional languages, but I want to achieve a lot of the functional properties. So I want to deal with data structures when I'm dealing with the network that are easy to reason about, that have immutability, that grow with monotonic state. It's a really nice way of thinking about the problem. How can I do that in a language like Java or C++ or C and make this work really well? But also, I want it to be super fast. So when I built this system, me and some other people, we were given the task of build the fastest messaging system in the world and to make it easy to understand. Kind of interesting challenge. Was it possible? We built data structures that had these properties, but they also performed really well. So let's look at how do we actually do this. So one of the fundamental data structures underlying this is we call the log buffer. And rather than using our tree structures that don't perform, we need some other structure that gives us the CRDT type properties, but doesn't have the memory access problems. So what do we do for that? Well, for the log buffer, we allocate a large amount of memory, and it's structured inside a memory map file. This is nice because we can use it across processes as well as across machines. And it's got a concept of a tail. So you add always at the tail. So this is where basic queuing theory starts to come in. If I'm going to add a message to be sent, what I do is I put it inside the buffer and I move the tail along for the next thing. I add something else, I move the tail along again. And we start to see we're just building up our state monotonically now. This is all kind of a nice way of doing this. There's a number of steps in it. It doesn't happen in one single go. It has to be broken down. We also do this without any locks. There is no concurrent overhead to this, is that it can happen completely independent of other things. And I'll show you how some of this neat stuff happens. So we need to move the tail. We need to copy in the message body itself. And then we need to put a header on top of that message. That header has actually got all of the information we need for doing the CRDT to go onto the network. So it puts us in a nice position here. You may say, well, do I just keep going forever, one big file? Not really when we want to look at this from a systems engineering perspective, because we end up with certain problems. We end up with lots of page faults. We end up churning our cache for the file system. We end up putting a lot of pressure on the virtual memory system of the operating system, and that slows us down. So we've got to respect that. How do we work with that again? Show some sympathy for what's underneath. Simple solution to that is, if anybody's ever gone backpacking, one of the things you learn quite quickly is you travel light. And one of the ways to travel light is you only need three things. You're always wearing something, you've got something being washed and something being dried. So it's wear one, wash one, dry one. Do the same sorts of thing with your data structures. So we have the concept of the active one that we're using. We've got one that's dirty, ready to be laundered, and one that's been cleaned. And we can just cycle around and use them over and over again. By doing this, we remove a lot of the pressure from the operating system. It's kind of nice when we do this, we can even have monotonic state. We just need to take account of when can we actually garbage collect. So we end up with some very specialized garbage collection for dealing with this, and it's nice when you can track a usage pattern. So how do we deal with the concurrent side of this? So simple data structure. What if we have multiple publishers? How do we manage those to deal with the concurrency and also to deal with the coherence and contention? Well, I said there's no locks, so how do we do this without locks? Well, let's say two separate threads or processes are sending in two messages at the same time, and we want to put them into the log. Well, our CPUs have got some very nice instructions that will do things concurrently and manage it properly. For example, I can increment the tail pointer on this. And I can do that with a single instruction on a modern CPU. And it doesn't require a lock. It does the whole operation in hardware as a single operation. Another thread can do exactly the same thing. Those have happened concurrently, not in parallel yet at this stage. Then along comes, we have now got our claims for where we can put the messages, because if I increment the tail and I succeed in incrementing that tail, the instruction that I issue gives me the value that it was before the increment succeeded. You know the length you've asked for, so you can take the successful case, apply the value that it was before, and that space is now valid to be used, and to be used completely in parallel without having to go through any agreement process. So what stages? One of the threads copies in the message. Let's say we've got the difficult case here of you're actually at the end of the log and you're needing to move to the next one because your active one now is full and we need to go and use the clean one. You put in some padding, and this is the responsibility of the thread that has tripped the end of it, so the one that moved the tail down below the white into the black here, rotates the log across, and you put in the next message. It's a simple protocol of interaction. So actually, agreeing protocols for how things interact is a really good way to make a scalable system. There is no central control. It just works based upon protocols of interaction and scales really nicely. So go forward. So obvious question might be, what's in a header? What's inside one of those headers that we put inside the file? If anybody's ever worked on the IETF standards for protocols for the internet, you specify your headers and your data structures for bytes like this, where you say, you're looking at the number of bytes, how we're laying out. Within this, we have a number of fields. Like we've got the length of the frame that's going to be on the network, versioning for the protocol so we can update it later on, some flags, and some other information in there. I'm not going to go into the whole detail of this, but what you need to take from this is all of those fields together will let me totally replicate this data structure from one machine to another and reassemble it and respect the properties of the CRDT. So it's a kind of nice way to do this. So, but now we got to deal with difficult questions. We're dealing with multiple things happening in multiple processes. Things can die, things can crash, they can go wrong. We got to design for this, we've got to cope with it in the right sort of way. So let's say we're writing a message and we fail partway through it. How do we deal with this? So the protocol for interaction for dealing with this without locks is, first of all, we write the length of the frame we're going to put the disk into the file, but we'll write it negative rather than positive value. So say I'm going to write 400 bytes, I'll write negative 400 into that field. And that lets me know it's not complete yet. But I know how much space is reserved, so if it goes wrong, I know what I'm going to have to clean up afterwards. I'll then write in all of the fields for the header. That can all happen in parallel, all nice and clean. Write the message in itself afterwards. Again, these are all just steps to complete. And then finally, flip the value from negative to positive, and now I'm complete. If something's reading this, it needs to just read forward through the data structure until it sees the header. When it sees a header value that's positive, it knows it's valid to read. If it sees it as 0 or a negative value, it's not yet complete. Doesn't need to do anything. You don't need any locks, no interaction. There's no need for an agreement protocol around that. Keeps it all very simple. So how do we remove this on failure? What do we do? Well, in the case of I've claimed some space and I'm going to go through the process of writing everything into it, and my thread dies or my process dies. How do I deal with it? Well, something needs to be observing this. So we need some sort of supervision style concept. We observe that this has gone wrong, and after a given period of time, we decide to take some action. So we see after this thread is never going to come back and finish this job. So what can we do? We see how much space needs to be dealt with. We move things forward accordingly. We mark this record as now being invalid, because remember with this CRDT, if it's monotonic, we can only increase in state, we can never remove. So we mark this as not being usable. This is the concept of the tombstone. We put it in here, and then we flip the header back to positive, and now the data structure can be used and continue onwards, but it's marked as this is not valid. You skip over it and continue doing work. And now we can easily progress with our data structure. So how do we replicate this from one machine to another? It's actually quite simple. Our frames that go onto the network had all of the data in the headers to say where they go in the data structure at the other side. It's all part of the structure. So a message goes onto the network, it arrives at the other side, you copy it from the network straight into the data structure. Very simple operation. Notice there's 2 pointers in this. We don't just have a tail. We have a concept of a rebuild pointer, and we have a high water mark. You start to see the obvious difference to these when I give you a simple case. So let's say message 3 arrives after message 1. We haven't seen message 2 yet. We know from the header where this needs to go in the target file, so we put it into the target file. Now we've got a high water mark, which is the highest point we have seen, but not necessarily being contiguous. High water mark from the terminology where you see water going against the wall by the sea. It'll be wet to the highest point, but it's not necessarily solid. The rebuild is the solid bit. We get message 2 comes along later. Now we're in a good place. We have a contiguous thing, and we can see that we've got all of the data all now in place. So what if a gap's never filled? So we get loss, and this never arrives. Well, if we just send a knack message for that, we can get it back again at that point. And by just knacking for things we haven't seen rather than positively acknowledging things, we can recover the loss. And so eventually our data structures become consistent between the different machines, and we can deal with any loss that happens to be on the network. So think about the layout now of this. So remember the structure of the trees and how we deal with it. We now have a data structure that can have concurrent read. We have immutability. We have all sorts of nice properties of the CRDTs, but look at it also, it's completely linear through memory. And remember how fast memory was to access in a sequential fashion? It's very fast compared to following trees and jumping around things. It makes a big difference to the performance of this. And then how do we know what state we're in? Again, sort of like monotonic counters come to the rescue here. We give a counter to every entity in the system. So the publishers of data, they have a counter of what position they've reached, and it's the absolute byte position along a stream. The sender that sends that onto the network, it's got a counter, receiver that takes it off the network at the other end, and then eventually up to having multiple subscribers. And again, because it's all immutable data, we can have multiple subscribers on the network and on other machines, and they can all coexist in parallel without having any impact on each other, so it scales really, really nicely. So kind of getting ready to wrap up here. I've covered the data structures itself, but there's a couple of things to think about, like shared mutable state in these things is really, really evil. And I know from building these things, it's one of the important things we can do to really get around a lot of our issues of reasoning and understanding about stuff. But we can't just jump to this without an understanding of the hardware and the network and doing the right sort of thing. When we get to deal with this, we have to change stuff. We have to mutate at times, but we can make this a lot easier if we only have a single writer. Don't have multiple concurrent writers to the same thing. If we do that, we end up with universal scalability law, dealing with the contention on it, and we also have to deal with the coherence of agreement. So it gets us on the complexity front, but it also really gets us on the performance front. So we've got to go with different ways of doing with this. Even better, go for shared nothing. So any design where you just don't share things, and if you do share, all you ever do is share readable versions of something, it scales and performs much better, but respecting the underlying hardware and how we deal with stuff. All of this is done just by using protocols and building on some basic principles. And one of the most important principles in this is build everything on monotonic state. It makes it so much easier to go forward and deal with this in all of the cases. We can easily reason about it. We can easily understand a lot of this. If you want an example of how this sort of stuff's done, it's up on GitHub. Aaron's an interesting project that you can play with. Like, how fast is this really? We can do tens of millions of messages per second on commodity hardware without any problem. We can saturate networks. We can saturate disks to the greatest ability that can go with this. And this is a totally different design than what's gone before. But what's kind of nice about it is It's a pure functional design, but it's also informed by what's possible on hardware and how do we do it in the right way. So you've got to put the ideas together in the right sort of way. And I kind of leave this sort of quote. It's kind of one of my favorite ones from Mark Twain. It's like so much in technology. We can't be an island. We've got to learn from other areas. We've got to grow up as an industry, and we can get better at this as we go. And on that, I'm out of time quite soon, so I can take some questions if anyone would like to, but if not, thank you very much, and thank you for having me.
Thank you so much. So I just want to mention that the later version, I think the latest version of the Akka Stream or Akka Remoting now uses your Aaron for the transfer thing. So I just want to plug that in there. But my real question is when you're looking at the -1 +1 like a flipping thing, right? Does that assume that at some point like someone needs to completely initialize the array to 0?
Yes, so that's a very good question. Whenever I talked about the 3 buffers, the active, the dirty, and the clean, we're moving forward. And so what we've got is a specialized form of garbage collection. Because we've got the monotonic counters knowing where all the subscribers are, all the consumers of the data, when we know that the last consumer has passed a point, we can collect that. It's now available as garbage. And we have as a separate thread that runs through zeroing all that out, so it's ready to be used again. The nice thing is it's, again, something that just happens in parallel. There's no contention. And the reason it can work really easily is because it's sharing this state that just goes forward monotonically. There's no complexity around it.
Thank you.
Sorry, I don't have a microphone up here, but I have a question.
Sure.
Okay? Sure. Okay. When you increment past the end of a file, you said the thread is responsible for rotating that file to the next.
Mm-hmm.
What happens if 2 threads want to increment at the same time?
Yeah, so if I repeat the question, if we are reaching the end of a file and we've 2 threads are competing to produce messages and they may deal with the file having to rotate, the protocol is very simple. So we have the tail counter that can be updated concurrently because we use a CPU instruction on x86. It's the x_add instruction. It's an atomic instruction that will apply that as a single instruction. What it will do is it will update the value to by the much you've asked for. So say I want to add 400 to it. It'll add 400 to that, and it will give you the value that it was before that 400 was added to it atomically. You can then look at that value. If the value beforehand is greater than the length of the file, you're the second one to increment it. If the value is less than the end of the file, but the end of the file is not far enough to fit your whole message in, so basically if you subtract the size of your message from the end of the file, if your pointers are ahead of that but not ahead of the end of the file, it's the responsibility of that thread to rotate the file to the next one, and it's very clear which thread has to do it at that point. Make sense?
Yes, thank you.
Okay. Sure.
You mentioned there's a supervisor that takes care of like changing the flags.
Mm-hmm.
What happens if it dies? Is there redundancy there, or and if so, how do you deal with it?
So it's a good question. So we have what we call the conductor. It's a bit like a watchdog in the system supervising what's going on. It's relatively simple what it does. Yes, it could die as well. You could have a tree of however many you want. We find that only one is usually sufficient. We actually haven't had a case where we've had the failure of that followed by the failure of something else. But you could layer that as many times as you want, and then you're into a probability game of how many levels you would like to have for how many supervisors do you have for the supervisor. And ultimately, you're going to go to, you'll fire an alert, and some human's going to get involved to make a decision if everything fails so far. Okay. So, thank you very much. Arigato. Thanks for having me.
マーティさんありがとうございました。